I'm Phill Brook-Carter. I'm a senior lecturer at Federation at the Gippsland campus. And I'm really just going to run through a few examples of the types of projects I've been involved in and some of the interests. I've broadly entitled it waste management because most of these projects that I'm talking about today are indeed about waste management. So we've done work on digestion of effluents for energy generation and for production of a cleaner effluent that might be then discharged onto pallets or environment. And I've done those both as a lecturer whilst we were at Monash, and some of those have continued. And we've looked at recently a project here with the East Gippsland Food Consortium, and I'll talk a little bit about that and some of East Gippsland water. So currently, I have one PhD who's completed and is now working as a postdoctoral fellow in Stockholm on Giardia. I have another PhD student who's investigating the pathology of Giardia as a post-parasite. And Emily is here today to also talk about her work, which is factors affecting pulp and paper waste processing. So our first sets of projects have really been involved with what was DPI is now that at Ellenbank in Gippsland. Essentially they were looking around, they have a large farm at Ellenbank, and essentially we were looking at the removal of discharge water from the pad, the holding pad, into lagoons generally on farms. Now you all know that, or maybe you don't. Dairy farms wash down their pads into a large lagoon. The lagoon stores the waste that comes off there, and it's usually mainly fecal matter. And the problems with it over time are that the storage fills up, but one of the major problems really from current thoughts are they produce an awful lot of methane, and they can also cause odors. But the methane is both a greenhouse gas, a very bad greenhouse gas, and a very useful gas for us to generate energy. So we've taken liquid discharges, passed them through what are called upflow anaerobic sludge blanket reactors, which is essentially a biodigester, which has microbial populations in it. The discharge is pumped through it. Microbial populations break it down. They produce gas in the form of generally methane, but also some CO2. And the effluent, cleaner effluent, is returned to the lagoon, and you can keep cycling your lagoon. Questions are, what exactly is in your liquid discharge from your lagoon? What are the best parameters to run your anaerobic digestion? Because this was viewed as a way of doing this on farm for each farmer, not at a very high-tech way. But this can be very high-tech or it can be very low-tech. And the idea of these were to look at more low-tech solutions that actually farmers might, in fact, use. No farmer's going to spend $1 million to build a high-tech plant to deal with the waste from his washdown pad. But they might buy a tank from Tanks R Us and seed it over time with liquid discharge, and that will seed it with bacteria, which will then act as a digester. And how much gas do you get? What's its composition? What's the energy value of that gas? In a dairy farm, you can use that gas to heat the plant, the water that you need in your plant. You can also, if you really want to go down that way, you can co-generate, use that energy for co-generation and supplying some of your own electricity. The second of those was very similar. We took the liquid discharge, only this time we fed it into algae tanks to produce, I suppose, a green product, which is the algae. Same sort of deal, except we took the algae for, idea was to take it for stock feed. Questions again, what's in your liquid discharge? Is that consistent over your seasons? And you find that it's not entirely consistent. Flow rate of the AD, its temperature, its operational parameters, how much gas, etc. But in addition, this was the more interesting part of this was how much algae can you grow out of this lagoon storage. What are the difficulties in actually growing algae? Algae are photosynthetic, so they use sunlight. We find there are quite a number of problems, which is why there are not vast fields of algae blooming all over the country on wastewater, because there's quite a significant issues, technical issues that have nothing to do with the biology of the algae. Then one of our most recent bits of research was with this East Gippsland Food Cluster, which was a consortium of Patty's Foods, East Gippsland Shire Council, East Gippsland Water, and we did 2 sets of trials for those. We characterized their waste and fed it into an anaerobic digestion trial, and there was a second in which there was a particular product called biomass digestion, which they wanted to evaluate how well it worked, because they thought they might buy it and use it in their system. So the stakeholders for the East Gippsland Food Cluster were, as I said before, and this is essentially a picture of the Bairnsdale sewage treatment plant. You don't really have to go through it and understand the detail of it. It's not that important at this point. Our part was to take the return flow from the anaerobic digester, mix it with the stakeholder waste, slurry it, screen it, and feed the fats, oils and grease back into their plant and go through their anaerobic digester and see what effect on the output of biogas and so on, and the running of the anaerobic digester. So we had sludge from the treatment plant from East Gippsland Water, we had household organic waste from the East Gippsland Shire Council, and we had food waste from Patty's Foods, and that was essentially pastry and meat pie fillings. And Emily and I diligently spent hours in a laboratory mixing these things together in various ratios, and this one in particular is not pleasant. And we got a lot of information out of running this digester. It was a very good project from that point of view. We looked at the stakeholder composition of the waste, their consistency of production of that composition of waste, and how could you handle that waste, and what sort of ratios to mix it with. Pastry, for example, I'll tell you now, as you're probably already aware of, if you add any liquid to pastry, it turns into nice, mushy, thick paste. It's very stringy. And pastry is full of fat, and fat really can drive an anaerobic digester completely out of phase and turn this into a big tub of rotting liquid. So you have to be very careful about how we manage it, and this is one of the problems we found out. The second part of this was really to take that stabilized sludge and then see how you could use perhaps composting to produce a stabilized soil amendment. This was not part of Emily and I deal. The last one is the biomass digestion. This biomass company, Singaporean company, who claimed to have a rapid digestion process. They don't claim it, they actually have it. It's called the rapid thermophilic digestion technology. And they quote the use of a set of enzymes to help with the digestion. This is the digester machine, that portable one they brought for us to demonstrate. We brought this from Singapore. They were quite keen to sell it to us. It has a little sort of rotating drum here, which is heated, and all of this business of the motors and engines to heat and turn the components in this very small digester here. So we took the same waste that we'd used in the previous trial in the anaerobic digester, the stakeholder waste, mixed it in various ratios, and worked to trial it in this. However, that kind of waste ratio didn't work in this machine, and principally because it required a really quite dry matter. And one of the things we found was that in these composition of trials here, various waste, meat, dough, cereal is sort of rough wood chippings, and digest, and some very digestate from the treatment plant, and some very fine sawdust. And you can see how we mixed them, and the requirement for sawdust was really quite high because it required this mixture to be very dry. It was also very energy intensive, and these enzymes, which were stated as being a natural cocktail, naturally occurring enzymes, work at thermophilic, which is high temperature phase. So this was operated at around about 70 degrees. Theoretically, it will do this, but in a practical sense, well, the pastry gummed up the machine so fast that they spend the next day scraping pastry out of the machine. So not all of the ones here that had any, these three here that had any significant composition of, sorry, you can see the composition of dough is very low. One of the objectives of this was to try and get rid of this dough, because that's the waste product from the patties pies. What this showed us here was that when you put a reasonable amount of dough here into the mixture, it just gummed up the entire works. Everything else had to be a tiny amount and a huge amount of sawdust, so really you were processing sawdust. So I'll leave you, turn you over to Emily now, who will talk you through a little bit about her own project at the Gippsland Water Factory, which is a water treatment plant.
Hi, I'm Emils Scholes. I spend my time at the Gippsland campus, although actually I'm not a student, and I also am part-time, so I spend half my time consulting on a range of wastewater issues and problem solving for industrial systems. So my project was based at the Gippsland Water Factory. Prior to coming to this PhD, I spent 5 years working for CH2M, an engineering company, and we started at the pilot plant piloting this process, and it ended up being a $300 million project which treats both the domestic wastewater for the Latrobe Valley and the pulp and paper, mostly pulping wastewater, so about 20 million litres a day of highly contaminated, highly coloured pulping wastewater. And Gippsland Water Factory is unique in that it uses a very low technology anaerobic lagoon coupled with a very high technology membrane bioreactor. And this is a world first. So this is the site, and ignore the strange visitors building down there. It's weird and round and very impractical. But so the wastewater comes from the paper mill, and it actually combines with waste sludges. Water from the paper mill is very carbon and sulphur rich and very nitrogen and phosphorus low. So it's a requirement that the primary and secondary sludges from the domestic system be input into the anaerobic reactors along with the wastewater influent from the paper mill. So the effluent comes up to the membrane bioreactor, but also there's biogas produced from that, and that goes through a desulfurization process and then is used to produce electricity. So I think it's about 250 kilowatt hours a day, and that powers about, along with the micro hydro that we have, about 40% of the plant's energy needs. So the membrane bioreactor on the industrial side here, the other side's a domestic one, is what my study was based on. And there's filtration cells, and then the wastewater is treated and goes to what's called the regional outfall sewer and out to a sea discharge some 80 kilometres away. So there's this test result which is called CST, or capillary suction time. And when I was asking Gippsland Water what they wanted me to study for my PhD, they went, well, the membrane bioreactor works really well, but sometimes we have these high cost, low treatability events, and we don't really understand why. And so my mission was to understand what these high capillary suction time events were. So capillary suction time is a simple chromatography test which broadly parallels the cost and difficulty and filterability of mixed liquor, which is the microbe soup that does our work for us by eating the pollution. So why do we care about this? Well, when we have a high CST event, the capacity of the plant dramatically reduces. We get about 20 million litres a day of effluent from the paper mill, and if you can only put 12 million litres a day through the plant, that rapidly leads to a rather large amount of water which begins to smell pretty bad. and fill up storages. Dewaterability. So a cheap day running the centrifuges might cost $5,000. Under a high CST event, this could go up to like $25,000. So that's a rapidly unsustainable situation. Also, a high CST event is generally in domestic systems thought to reflect microbial stress. Also, under a high CST conditions, the membranes themselves, which are about $6 million worth, failed more readily, and you have to spend a lot of, put them aside for a time so that they can be cleaned, and that has a chemical cost, but then you also lose capacity in your plant. So for these quite good reasons, it was really important for Gippsland Water to understand what was going on in the MBR. So when I sat down to think about the areas that might actually be influencing CST, there were 6. So what's coming in to the plant, so what's coming from the paper mill, what we're doing inside the process, so in terms of what kind of flows we use, what kind of dosing we have of various nutrients, that sort of thing, to the physicochemical properties of the mixed liquor, the microbe soup itself, so things like hydrophobicity and viscosity and suspended solids content. Funnily enough, the microbial species present in the microbe soup, what could be quite important, how well and how active those microbes are, and finally microbial or generally extracellular polymers that come out or are concentrated up in the process, because you have a membrane which retains all solids. So the membrane's actually about 0.04 micron, so anything that doesn't fit through that, that filter actually gets retained in that mixed liquor. So I'm about 3/4 of the way through my project, and we've identified the causes and mechanisms of the high CST event, and this has essentially been traced back to a discharge of what's called black liquor from the paper mill itself. So this is a very high pH, very highly coloured and colloidal substance, which on a normal day they would send all of that to be burnt, and so they can recover the caustic from it. But sometimes they have uncontrolled shuts, and then we would get this black liquor. So we were able to understand that's where it was coming from. The problem with that is that they could discharge that for 2 or 3 days, but because it couldn't physically get out of the plant because it was colloidal, it couldn't go through the filtrate, and it didn't come out in the centrifuge because it stayed in suspension, there was no way of it actually getting out of that plant except via very, very slow, gradual time. So we formulated a development of an early warning plan, so we know that if the monovalent to divalent cation ratio changes, in other words, we have less calcium and more sodium, then it's more likely that this is on its way. If we have high colour, this is more likely it's on its way. And we've developed a bunch of operational management actions whereby we can try and minimise the effect of the black liquor discharge. I've developed some standard parameters, which are a little unusual, for monitoring the MBR, and I've published a paper in Water Research about that. And I've identified key microbial populations, some of which are undocumented to science. So as part of my work with Federation University, I'm part of the Advanced Industrial Analytics Centre, which is co-located with the Carbon Technology Research Centre with Dr Phill Brook-Carter. And I also do some consulting of my own to various water authorities and different companies that are interested in scientific monitoring, setting up sampling programs, what should be monitored, how to train their operators on how to do basic testing. And my company, EnviroMicroBio, looks at microbial ecology and brings biotechnological solutions, particularly for monitoring either biomass that you want to do your work for you, or for populations that you'd rather work there. and that are a hindrance to your manufacturing process. Also do use next generation sequencing to understand the microbial populations. So whether that be, why is this biofilm here, and how can I get rid of it, to does my fertiliser have an impact on the microbial populations, and is that a positive change or is that a negative change? So, that's me.